Oh, hey. Yeah, AI can do a lot of stuff well. Um, what I think a lot of people kind of, I'll say, miss the mark on with AI is that it's only as good as the person using it, because if the person using it doesn't have any idea what it's spitting out or if what it's spitting out is accurate, then the solution it spits out never works. And I know that sounds obvious, that like if it spits out a not working solution, it's not going to work, but a lot of people don't really get that. Like, I've been in situations where people have submitted clearly AI generated code for me to review, and it's not fun because like I know it's AI written and I know it's wrong, because I know what the task was and I know how the solution should go, and I can research it and I can see, hey, this is actually just the wrong way to do it. Yeah, close enough is the people who usually say close enough don't really know how close they are to begin with. So like, for instance, if I'm coding, I don't know, something for, it's really hard because I know these examples aren't close enough, but like, I don't know, if you're coding something and you're not really using any proper auth library, and like you're not even doing like bare minimum things like salting, but the authentication technically works, it's like, oh, it's close enough. It's like, well, no, like you don't really know what you're missing. Like, you don't really know how close you are in a lot of cases. And when you do know how close you are, you generally like, you wouldn't necessarily say close enough. You would say something like, this is the only thing that's missing. I mean, even just like not understanding how file blocking works, you can double your IO operations in some workloads. So like, close enough can sometimes literally double the amount of read-write calls you're making to a disk just because you didn't math the right number. So a lot of that stuff actually does really matter. We just don't talk about it for some reason. So what I wanted to do today, I thought this would be fun. We'll see if it actually is. But what I want to do today is I want to take a piece of code that I didn't write, a piece of code that I looked at briefly. I understand it, but like I don't really understand it, right? Like I understand the high level, but if you told me to just go code this, I couldn't do it. I don't know enough to code this. I understand it when I read it, like the high level, what it's trying to do, but like there's a difference between knowing and understanding. I don't understand it, I know it. So what I want to do is I want to try to take Copilot, and I just want to give it this code, and I want to try to walk through this with Copilot and see if we can understand it. And we'll kind of see how this goes. I don't really have a metric for how I'm really gonna follow this through yet, but I think what we're gonna do is we're just gonna throw it into Copilot on like the quick response setting, and then maybe we'll look at think deeper, and then after that maybe we'll see if this is like a, I don't want to say famous, but like other people have looked at this code, other people have probably reviewed this code. We can probably find some other source material explaining this code, and then we'll kind of see how the AI did and kind of see if this was worth doing or not. I'm kind of suspecting it'll get some things right and then other things just egregiously wrong, and it's going to be just as confident the whole time. And that as the reader, unless it's just like blatantly obvious that it's wrong, like recommending a syntax error or something stupid, I think it's going to look just as confidently right, and will probably, or I guess would be mistaken by other people as a correct answer. That's my guess for where we're going to end up here. But yeah, we'll see where it goes. This is still all in the name of the chess thing that we're making. One thing I kind of started doing, I'll bring it up here. I haven't figured out how I want to, I'm telling you guys, this is like the guinea pig stream, okay? Like, I have no idea how I want to set these windows up. So what I've got going on right now, which is like, it goes against like everything I've done as, I don't want to say like a broadcaster, but like as a streamer, I guess. I've got an ultra wide monitor here that I can't keep in ultra wide mode because I have to stream at 16:9. And my day-to-day life, I have so much more screen real estate that I just don't know anymore. I don't know where to put these windows to see everything, so bear with me. What we're going to do today is we're going to look into this billion row challenge. And as a research goal here, I want to research the first place submission, and this is what we're going to do with the AI. We're going to look at the billion row challenge. And see if the AI can explain it to us in a way that we kind of understand what's happening. Is this Java? Yeah, this one is in Java. The goal of this project is you have a billion rows of city, semicolon, temperature, and you have to sum the temperatures as fast as possible. You've got a billion rows. So this seems like a really good, we'll say, project. I don't know. It's not really a case study or anything like that, but this seems like a good thing for us to research because we really want to do fast I/O. One thing we know for sure is that they use something called unsafe. And unsafe gives you like a lot lower level access to the memory than the Java API typically does. So they will use unsafe to quickly allocate or deallocate things, or quickly get access directly to the memory, and a bunch of other things like starting up threads. I think they use unsafe for. They use it for a lot of stuff, and that's because in earlier versions of Java they didn't really have any API related ways to get into a lot of this lower level stuff, so they made unsafe as like a back end like administrator tool, let's say. In newer versions of Java, though, they're trying to phase out unsafe, but it's really hard because Java doesn't want to put like this fork in the road where like you can't, to make it harder to upgrade, basically. They've already done that a couple times with major upgrade decisions where it's kind of hard to upgrade to the next one. So they don't want to do that as, trying to think of I think Python 2 and 3 was the example where there's just a lot of stuff that's not compatible. They're trying not to do that. So they're trying to implement things like var handle and foreign function and memory APIs. So like once we learn kind of what they're doing here with unsafe, yeah, there's a lot of cool stuff like that, where you can kind of like pre-cache things. If you just know where things should be, you can usually bypass how the API wants to handle it because you know something will be there. So what we're going to do is we're going to look at their use of unsafe, and we want to try to map that to, hey Turskwill, we want to try to figure out how, instead of using unsafe, we can use var handle or foreign function memory APIs. But I think the real question is, what do Copilot say about this? Let's get right into this. Can AI help me understand this? Also over here, this is the note-taking app I've been using recently called Obsidian. So we're going to take some notes. We're going to see what we can get. We'll put this here maybe. We'll figure it out. Like I said, I don't know where to put things yet on stream. I'm not used to having smaller screen real estate. So the last time we were here, remember we did buffers. So like these are my notes on buffers that we took last time. NIO channels. So I'm hoping to keep these notes, and I can even link them back to VODs. This is all like query based too, which is really cool. So like this shows up because, so like this is the file name. This shows up because in this file, if I turn it to source mode, I have a metadata tag here for the VOD. So I can just pull them all back. Oh yeah. And then here's last stream, I talked to an AI about asynchronous. This is why I don't like AI. So Can an asynchronous file channel be used with a direct buffer? Yes, absolutely. Okay. Yes, absolutely. And then it says, where is it? It says that you, so it says using a direct buffer is okay. Then I say, so what's a memory mapped file? Because somewhere it says that you can't use direct access. I'm just skimming it right now. But yeah, then I say, but a memory map file is direct access and an asynchronous file says that you can't do that. Then it says, no, you're absolutely right. So it tells me, yes, these two things can be used together. And then I ask for a bit more clarity. And then it says, yeah, but you can't use it with the thing we were just talking about. And then when I confront it with that reality that it just told me about, it's like, no, you're right. Oh, well, I don't want to be right. Like, I want to find the right information. I don't want to be right. I want to find what's right. So let's get into the, today we're going to use AI to analyze the oh, do I actually have to? There. Billion row challenge. So, also, so this is for anyone who's not familiar with Obsidian. This is why I really like it, because now I can just type in Markdown and get some nice notes out. So let's jump over to the billion row challenge. Let's get the first place. Oh, that's the wrong button. We want to control click. No, we don't. Okay, hold on. Oh, it does. What don't you like? Great. I've broken it, everybody. I don't know what I've done. We'll just open it in a web browser. Oh, light mode. Ah! Ah! GitHub, please. There. What? No. What? Okay, sorry guys. We're not going to be here for long. We'll just download the file and continue. Download. Done. What? Okay, it can't be a Java file because that's a problem. Text. The file's not that big. Oh, there. So, let's see. How are we going? So let's see. I am trying to learn about efficient file I/O. The file I have attached is the Java code for the winning entry to the 1 billion rows Java challenge. Can you please explain how this solution works and what I can and what I should learn from it in order to make my own projects more I/O efficient? So let's see what, let's see. Now, from here, we need to we can use other AIs as well, but let's start with Copilot quick response. And up here, we will make a new note, and we will call it 1 billion row challenge explained. Quick response. Now the reason I'm keeping these like this, where I like keep the question and keep the answer, is Obsidian can fully search things. So like, I don't have an example right now, but I've got things like Olama installed, so I can actually like search images and stuff too. So like, it's super cool. When you index it with a lot of information, you just kind of have a really efficient note system that you can come back to over and over again. So let's see what Copilot says. We're going to go through this bit by bit, or I guess line by line. This is a masterclass in high performance I/O. The winning solution to the 1 billion row challenge is a brilliant example of how deep system level thinking, memory management, and parallelism can be harnessed to process massive data sets with astonishing speed. Okay. So, you know what? Let's start with screw it. I don't really care. I don't care for headings to be super accurate. So we'll do this. High-level strategy. This solution processes a huge file. We don't need that. Containing 1 billion rows by... We're also going to try to keep this marked up similarly. I know this seems like we're slowing down here, but again, if this turns out to be right, we've now got some pretty good notes. But we're going to also need to be able to skim this really quickly later when we're doing other research. So the marking up might seem like a waste of time, but I'm hoping it'll help us later. And if it doesn't help us later, then I don't know why the AI decided to bold these things, if it didn't want me to know. Oh, hold on. I have a sound for this. We'll just mute the music for a second. You guys see that bot in chat? You guys see that bot?
Fuck you.
I don't think that played. Oh, did it? I think it played for you guys. It didn't play for me. Did you guys hear a fuck you? I didn't. Back to music. Yay, played for you guys. Okay. Good. Hold on. I'm going to play a sound again so I can figure out where mine is. But I can do that. Let me, is it?
Oh, hi. Thanks for checking
in.
I'm
This one.
still a piece of garbage.
There we go. There we go. I found it.
Feels great to be doing stuff.
Okay. I don't know why it's so quiet today, but...
Fuck you.
There we go. Now I can hear it.
No! Wait, what?
We're good. Okay. Sounds work. Okay, so high-level strategy, using memory map files, spawning sub-processes, parallelism, dividing the file into segments, avoiding object creation, and garbage collection. That's, I think, so 2 things I need to do. Memory mapping file, avoiding object creation, and garbage collection where possible. Okay? I don't care so much about, I mean, I want to learn about it, but in terms of my solution, I don't care. So maybe we should make notes for that too. So can I make one of these right here? I can, okay. So we're gonna say, what kind of a tag can we put here? We'll just put I'm blanking on a term I can use to put here to remind myself later that this is something that I'm gonna do as well. We'll put implement or something. Implement. There we go. Okay. So, key techniques to learn. So we're already on the right path. First one. Key techniques to learn. Memory mapped I/O. Okay, AI, what are you going to tell us about memory mapped I/O? There we go. I don't think we need that bolded when it's a heading like that. So, instead of reading a file line by line or buffering in chunks, that's what we do right now. That's what we do right now. So what does this do instead? So it uses this instead. Okay. So file channel map mode read only 0 file size arena global address. This maps the file into memory, allowing byte level access without copying the data into the JVM heap. That's super important because a lot of our time is spent on I/O. So this is now something we're going to block quote. Where is... There we go. Sub-processes for cleanup. And don't give us an example of that. We wouldn't want an example of that, right? See, this is where immediately, like, I'm not super... You're getting close to halfway through this answer, and I don't really feel like I really understand the solution. I don't know. We'll try again, but I think AI may be taking an early nap. We'll read this here in a second. This one's really short and doesn't have a code example, so I figured, hey. Oh, there we go. We can use a call out. What's the call out look like? There we go. Can I use a different... Can I use the word lesson? Will that work? Oh, it does work. Okay, cool. So let's do that up here, too. What was the... We will do another call out here. There we go. That looks even nicer. Look at that. The process spawns a sub-process with -- worker... Like, that doesn't tell me anything about... Like... We can link this to the code here in a minute, but, like... That doesn't really tell me anything. Right? Let's see this one. Now, people in chat, do you guys want to see me try to reason with quick response, or do you guys want me to just, like, jump to a different response type after this? What do you guys think? Okay, we'll put that. We'll put that in here. Segment size 2 megabytes. Okay. So the file is split into segments. Now that part I'm kind of interested in, but I'm really gonna have to look at what they do. Like, I'm interested in it, but I'm not. It's like I'm not interested in it necessarily if it makes it. Let me see. What's the word I'm trying? What am I trying to say here? It seems really complicated to split the file before processing because I don't know how you find your bounds asynchronously. If that makes sense. Unsafe memory access. So this is something that, like, we also kind of want to do, but not really. Like, we don't want to use unsafe, but we want to use the new implementations of unsafe. Like things that try to achieve the thing that unsafe was achieving, but we don't want to use unsafe. But let's see if this even bothers to tell us much about unsafe. Okay. No, I mean, not really, but bypasses Java safety checks. And allows for raw memory access, which is risky but extremely fast. I mean, you kind of get over a high level idea of what's going on there, I guess. It doesn't really explain a lot, though, does it? But oh boy. We're almost at the end. Do you guys feel like you know a whole bunch about this? Do you feel like you could go write your own now? I don't. Now, I know, like, I do understand that, like, I'm kind of just ragging on the AI here a little bit. I could poke it and prod it and try to get a whole bunch more stuff out of it. But if I'm going to be completely honest, a lot of people don't do that. A lot of people just read what's there and they decide if that was a good answer or not. So that's kind of what we're doing here. Just because that's how I believe a lot of people use the tool. So yeah, the code uses sunmisc unsafe to read memory directly. Great code example. This bypasses safety checks is really fast. Parsing numbers without conditional branches avoids CPU pipeline stalls. The code uses bitwise operations to look up tables to convert. Okay. I mean, that could be faster. I mean, obviously, but I don't know if that's necessarily something that we should be, like, I don't know if that's necessarily like a lesson we want to learn to just implement, right? Sure. I mean, maybe it's, but like, why is it done that way then? Like, is there a reason why? Sorry, I'm thinking at the same time. Is there a reason why I would ever want to actually do that, though? Like, how much faster is it? What's the trade-off? And I love how this is just, like, advocating for you to just, like, yeah, use custom hash tables. Don't use the ones built in. Just use custom ones. That'll be fine. Instead of using hash map, the solution uses a fixed size array, and the computer hash indexes the compute. Wait. Instead of using a hash map, the solution uses a fixed size array results and computes hash indexes manually. Okay. But like, that's not sure. Custom data structures tuned for your workload. Yeah, I mean, if you make something specific for something, yeah, sometimes it's better. But like, I think that's also because you're not, I mean, we'll look. I want to see how they're doing it for sure. Efficient string handling. This is one I kind of care about. This is something I also need to do. So let's, oh, yes, great. We get a single sentence on it. City names, parsed using a bitwise mask and stored as 2 long values. Okay. I mean, theoretically, we could do some of that, but like, to avoid creating string objects. Yeah, like, I mean, but eventually you have to. The other, so we'll take this time here while we're parsing through this, like, I don't know, in my opinion, this is so far, like, what we've got right here is kind of a, well, let's see what it says we can apply before I say it's a waste of time. 3, okay, so this is going to be a level 3 heading. Here's what you can bring to your own projects. Am I going to have to ask it for a markdown table? Give me the last table in a markdown format so I can copy it. Okay, cool. So this is what it says. I mean, all of a sudden I don't like these anymore. There's nothing I can really learn from this. I knew all this already. This doesn't explain the solution to me. This just gave me a bunch of high-level concepts. I mean, sure. I don't know. I'm very unsatisfied with that answer. Hold on. I don't like that. A super high level overview of the concepts involved. No code commentary, and the few examples provided weren't really helpful. Overall, I didn't really learn anything from this response. So, we're going to play that same game again. So we're going to copy the exact same question. New conversation. Think deeper. Let's try with think deeper. Make a new note. And this is going to be think deeper. Okay, Copilot. This is round 2. I'll be honest, round 1 kind of sucked. Let's try round 2. Okay. Look at that. That's already a bit better. Yeah. Maybe. That's also not great. What do you guys... I mean, maybe we got to tweak our input query, but I don't know. I thought this was pretty good. I'm trying to learn about efficient file I/O. I have attached some code Please explain how the solution works. I don't know. I was kind of hoping to get like an actual explanation of how the code works when I asked how the code works, but maybe I'm asking for too much. Maybe I'm just being unreasonable. So this implementation squeezes maximum throughput out of modern hardware by combining memory mapping, low-level byte access, branchless parsing, and parallel work stealing. It spawns a short-lived subprocess to map the file off heap and let the JVM quickly unmap it, then divides the file into fixed size 2 megabyte segments that a pool of threads processes concurrently. Each thread uses Am I missing a word here? Hold on. Yes, I am. Unsafe. Copilot doesn't always let you copy everything for some reason. I don't know why. To read 8 bytes at a time. We're also going to be missing result after per city, which is here. And sorted pre-map. We'll get back to reading here. It's just I don't want to stop every time and be like, where's the word? Okay. Unmap it, divides it into 2 megabytes. Each thread uses unsafe to read 8 bytes at a time, applies bit masks to find delimiters and digits without branches, and updates minimal per city result structures in an on-heap hash table. At the end, each result from each worker are merged into sorted tree map for output. Okay, that's a rough English, let alone a rough answer. Okay. So go on. Memory mapping. Again, we just kind of throw out this worker flag like this, but we never really like explain where it comes from or how it works. The workers call. Oh, this is getting a. Can I? There's got to be a better way to copy all this. How about this? Okay, so let's get the question again. Okay. I don't need this. There. We are going to we're just going to pop these down a bit. There we go. Okay. So I will probably go back and update this later with okay, so memory mapping, the sub-process trick. The main process immediately forks a child with the worker flag. The worker calls filechannel.map via the foreign memory API area.global, giving a native pointer address to the file bytes. When the main exits, the child can perform the unmapped cleanup without blocking the original process. Memory mapping provides any JVM level buffering or syscalls per read, or avoids, sorry. Memory mapping avoids any JVM buffering or syscalls per read, achieving a near zero copy IO. That so far out of both of the things we've read, is probably the best piece of advice so far, in my opinion, for what we're trying to achieve. Parallel, so yeah, I like that one. Okay. Parallel segment processing uses runtime.getRuntime.getAvailable processor threads. So it uses all available threads. An atomic long cursor work steals fixed 2 megabyte segments. Each thread atomically grabs the next chunk. That's an opaque statement. Segments align with new line boundaries by scanning for /n via bitwise detection, ensuring no line is split. That would be a good strategy. Maybe. This is where you kind of get into like find the new line, go backwards kind of stuff. But within each segment, the code subdivides into 3 sub-cursors, so a single thread can use instruction-level parallelism. That's another opaque statement without an example. I'm calling these opaque statements because, like, remember, I asked it to, like, explain it. Like, explain how this solution works. So, like, sure, you could say that it's kind of getting there, but, like, again, this brings me no closer to doing it. And like I said earlier, we can argue that, oh, well, you don't have the code in front of you, but, like, let's hold on. Let's I'll move this up here for a second. Let's do that for a minute, right? So let's actually, you know what? We'll copy this out because this is, I don't like the light mode. We'll do this in so how do I decrease? So let's try to find some of this. Memory mapping the sub-process trick. Let's find the worker flag. Okay. So we're recursively calling ourselves, I guess, and hoping that the very first time, like when you kicked it off in the terminal, that we gave it a... So, like... Spawn worker. So let's find spawn worker. Does spawn worker call main? And it adds another worker. So... Worker... Add command... So, like, for me, this is an opaque statement because there's no way to kind of know what's happening here. It doesn't really explain what's going on. So, if the array length equals 0, meaning there was no arguments, and it's not equal to the worker, spawn a worker. Oh, I don't have access to the Java docs because this isn't in a Java project. And process handle. We got an array list of strings. If command. So now we're just kind of looking. Info command if present worker add. We're going to add it if it's present. And we're going to get the args, and then we're going to add worker to the end of it, and then we're going to start a new process. Right, so this looks like recursion. And trying to find. We're gonna add the args. Where's oh, args are here. Okay. And then otherwise, we just come down here. Okay. And we get the number of processors. Is that this here? Yeah, so now we're here. So all that, this here, doesn't actually really get us what we're looking for with the memory map file thing. So like that's kind of a like that's not really, right? It's not quite what's going on here, because that worker, the worker calls this, not really. I mean, when we do the recursion and we get worker, we end up coming down here, because if it doesn't have worker, it just spawns worker. But like, I don't know, maybe I'm the crazy one here, but I kind of would have liked to have seen some of that in my response when I'm asking, hey, how on earth does this work? Okay, move my chats over because I can't see them anymore. There we go. So, let's find the foreign this doesn't use the foreign memory API. I don't think. Oh, area. Where is this? Oh, there it is. So it gets the start of the file. Sorry, I'm just dying. So it gets the start of the file by using map and 0 file size, get the address, and we add the so get this. Is this the memory address? Yep. So get the address. Address plus size equals, like, that's the offset that it ends on. So like, if you start on memory address 0 and you've got 10 bytes, your next, you know, you've got from 0 to 9, right? If you've got 11, you've got A. So the next byte would be B if we're doing addresses, which are in hex usually. There's our cursor. An atomic long cursor steals the 2 megabyte. I mean, kinda. Again, I don't think that is a good explanation. Segments align with new line boundary. And again, not that I have a better explanation yet. I'm gonna have to research it myself. But like, so far, I'm not impressed with what we've gotten. Segments align with new line boundaries. So, where's our new line check? Red. Measurements, min, max, max name, max cities, segment size, hash table, so that's all fine. But I don't see a definition of a new line anywhere yet. Accumulate results. There's our new line. But we Where's our new line method? Okay, here we go. So gross. Get the previous long. Current word is the previous while true. Love it. Wait. Oh, there's the break. Current word bitwise operator. That input minus that bitwise shift. Good. That's gonna be fun. Okay. So again, this is a lot more. This is the difference between knowing and understanding. This is what I meant when it's like, I know what's happening, but I don't understand what's happening. I'm still kind of going to have to figure out what's happening here. This doesn't really help me. And, okay, let's find the subcursors, I guess? Is that... And again, I'm not critiquing this code. I'm critiquing the AI's explanation of this code. Where are my three... Where's my three sub-cursors? Oh, there's my three sub-scanners. Okay. Scanner wraps unsafe. Reads get long. Whoa! Okay. These are detected by a XOR with the delimiter byte repeated. Subtract mask and... So wait. Isn't that what this was trying to do? Okay. An old bit trick for find any match in a word. Okay. Decimal numbers are parsed branchlessly. Find the byte offset of dot or space. Okay. Bit shifts and multiply by a magic constant to accumulate hundreds, tens, ones. Then apply a single mask or a sign mask. Okay. Like, that kind of makes sense. We're not encoding or parsing. We're using bit shifting to kind of do that all with... Jeez, one sec. I don't know why, but my throat is scratchy today. Not in like a sickly way. Maybe it's because I'm talking a lot. But I have been drinking as well. Okay, so avoids character loops and unpredictable branches that stall. We might have to look at this a little bit. Hash base, aggregation, and collision handling. Each thread keeps a fixed size table, 117 entries of result objects indexed by hashing the city name words. Okay. Where's that? Is that this? Maybe? Where's min and max? Okay, here. collisions use open addressing with a stride of 31. So like that would be a good thing to like maybe elaborate on. In full name comparison in 8-byte chunks. After parsing, each worker emits a list of results objects into a shared array, which the main thread merges into a sorted tree map. So I'm in about the same spot as I was before I read both of these, which is I understand it's using hashing, branchless parsing, multi-threading, and memory map files, but I want to understand exactly how this is, the code is working, not like a one-line summary of things. So we're going to give Copilot one more chance. Okay? We're going to use the deep research this time. Now this one can take a while. So we'll see how long it takes. Copy? Why can't I copy this? It worked every other time. Oh my goodness, I really am dying. It's okay. New conversation? What is going on? More options. New conversation. Does it not like my file anymore? Wow. Okay. So what if we there we go. Oh, deep research just doesn't take a file. Damn it. Okay, so it's not going to do exactly what I want. This is okay. We will try it another way. So this one is going to be deep research. So the other thing we need, okay, so now, what level was that? A level 3? Okay. This was the Think Deeper. Okay. A little bit better. However, this still lacked any real connection to the source code. If you knew exactly how it worked already and understood all of the concepts, maybe this would be a good summary. But as a means to learn how it works, or as a means to learn what's actually happening, this was a pretty bad summary. So, for deep research, we're gonna have to actually like just tell it to go look it up on its own. I am actually, let's see what we're gonna have to change this question a bit. I'm trying to learn about a efficient file I/O. I would like to learn lessons from the winner of the 1 billion rows Java challenge. Can you please explain how the winning solution works and what I should learn from it in order to make my own projects more I/O efficient? So hopefully this will go look it up, and if it doesn't, then I think Copilot just loses. But this could take up to 10 minutes apparently. So, browsing and analyzing sources. Great choice. This challenge is a gold mine of performance insights. I'll dive into how the winning solution of the 1 billion row Java challenge achieved its remarkable efficiency, especially in file I/O. Expect a detailed breakdown of the techniques, code-level strategies, and practical lessons you can apply to your own Java projects. This will take a few minutes, so feel free to step away and check back later. Okay. Sure. We'll come back later. In the meantime, let's look at what they're talking about here. So it's still browsing sources. It's not even writing the report yet. We got licensing stuff. Solution. Wait. No way. Is that not what this said? It spawns short. I'm sure I read this exact thing a second ago. Hold on. Did we not read exactly that sentence earlier? A child worker process. Oh, maybe not. Maybe not exactly that. But this looks very similar to what we just read, and like the AI just kind of slurped in this comment. The solution starts a child worker process for the actual works such that cleanup of memory mapping can occur. While the main process already returns with the result, the worker then memory maps the input file, creates a worker thread per available core, and then processes segments of segment size at a time. The segments are split into 3 parts, and cursors for each of those parts are processing the segments simultaneously in the same thread. Results are accumulated into result objects, and a tree map is used to subsequently accumulate the results in the end. Okay. There's the credits for who came up with the solution. Okay. It's still browsing and looking at source code. You know, though, I would be like pretty darn happy if, let's see, anybody watching us today? A couple people. Hope you guys are enjoying the stream. See, look, we're still going. I don't know what I really expected the AI to do, but like I kind of had higher hopes than the nothing that I feel like I got. So hopefully the deep research mode will kick in here and help me out, because otherwise I gotta go start all over again with my own research, which is what I expected anyway. Where I kind of expected this to go was roughly where it's at right now, but I kind of hoped that I would learn I kind of hoped we'd get longer stories instead of bullet points, so maybe I could glean a bit more into it. But like, what about this 3 cursor solution? Like, why is that good? Why is that fast? Why would I want to consider that? Why are you telling me that? those are kind of the questions I was hoping to have answered, but we did not get them answered. We can turn Zen mode off here. So for anyone not familiar, let's go over the let's go over the project again real quick. What are we doing? We're trying to make a PGN deserializer. Deserializer. Jeez, I can't even speak. So what that means is taking a game like this. This is portable game notation. Now I really can't speak. This is portable game notation for a chess game. And what we're trying to do is process millions of these as fast as possible. I think we can safely put this over here for a little bit. Maybe or not. No, there we go. I don't want it to be huge. Oh, now it's not always on top anymore. It was earlier. Okay, I'll put it on the other screen then. Jeez. What we wanted to do is we want to parse out these tags into what the tag name is, what the value is, and then we want to parse all these moves out. This one looks pretty easy and it's not too bad. However, once you get into a real game, that kind of changes. So immediately we kind of notice that this doesn't abide. Oh, that's not the file I wanted to open. That's a big one. This does not adhere to the 255 character line limit that's in the PGN spec. But Lichess is one of the most used chess websites. So I can't, even though they ignore the spec, I still have to support them. It probably makes file storage smaller, which is why they do it. But like now I need to worry about, this is a glyph. So like if you're familiar with chess, like the brilliant move sign, they look like this, $sign number for what glyph it is. Anything in between these curly braces is an annotation comment. This ... means white's move was back there. And then we look at the black's move. Where's the next thing that I would want to show? Right here. These parentheses here. They denote a secondary line. So it's like, this isn't what I actually played on move 4, but like if I was studying or analyzing my game later, I might say, okay, well, instead of playing whatever I actually played, I should have played D4 here. And this is what that would have looked like, which would have resulted in something else. And you can have as many of those as you want, and you can have glyphs in them, and you can even have comments. Inside this square bracket cal thing, so my editor's jumping all over the place. Let me get back over to that. I can't find it. That was an arrow anyway. Whoa, that's not what we want. Go find. So what this is a yellow arrow from C1 to G5, a red arrow from G5 to E4, a red arrow from G5 to F7, and a red arrow from C4 to F7. All on that one move. You'll also notice it's wrapped in those annotation tags, the braces. It's like we have to parse all that out when we're reading this. So like it gets harder and harder the more you kind of keep going. This is still thinking, which, I mean, I have hope. I have hope that it's going to come back with something better. But yeah, this one does take a few minutes. I kind of wish I would have, I mean, we'll be able to tell by going back and watching the VOD later. Kind of wish I would have written down what time that started at so that I just know. But yeah, I'm hopeful that this one will explain it a bit better, because of how long it's taking, and it tells me right here it's going to give me code level strategies and expected detailed breakdown of techniques and practical lessons. So like, I'm really hoping that this one does better than the first two. If there's another free AI we want to try, we can do that too. But Copilot's my go-to when I'm using one. Like I said, I like to use them closer to Google searching than doing any of this stuff. I usually use it to generate a list of sources that I can then go read, or I'll try to trick it into arguing me down from an idea rather than telling it to tell me what's best. It's hard to explain. I'm not like anti-AI, but I'm anti the way that people are using AI a lot of the time. So like, I don't like coming to AI and saying, how do I do this? It doesn't know, okay? It really doesn't know. And it doesn't know what it doesn't know either. So I'm not a huge fan of saying, AI, how do I do this? Or AI, do this for me, because it doesn't know. But what I do like to do with it is say, okay, here's a solution I've come up with. Tell me every conceivable way that I'm wrong, and then I'll make the decision on whether or not, what I'm going to do. So I'll use it to argue myself down from an idea rather than generate the idea or bolster the idea to make me feel good about it, right? I think that's really the difference between people who use AI well and people who don't. If you think the AI knows more than you, like, how do I word this in a way that doesn't sound insane? Like, clearly there goes my voice again. Okay, hold on. I'm going to do a BRB while this is... Oh, wow, is it done? Okay, this is done now. Okay. Let's go through it. But what I was going to say is... before my voice gave out, what I was going to say is, clearly the AI has access to more information on the internet than I do in my brain, but the second you believe that the AI knows more than you about a given topic, just surrender. Like, you've already lost. If you don't have the capability to learn what you're asking the AI to summarize, you're just blindly guessing. You're not getting smarter. You're not researching. You're blindly accepting what the AI is telling you. That is what we're doing right here, by the way. We're blindly accepting what the AI is giving us right now. But why are we doing that? We are blindly accepting what the AI... I don't think I can just copy this report either. We'll see. Although I'm not super... we got a couple code level things. We'll copy that answer, and we're going to shove it right here. Okay, so let's get our prompt. So right now we are doing exactly that. We're blindly just AI, explain, help, I don't know, you know, what gives. So far, hasn't been a great experience in terms of learning anything. So far, it's kind of just spit a bunch of bullshit out and stuff happened, right? So let's go through this. Let's take a look at it. See if this one's any better. But I guess closing off that previous point, if you're incapable of learning what you're asking AI to summarize for you, you're not doing yourself any favors. You need to be able to understand the output from the machine. If you can't understand the output from the machine, it can't be trusted. So when we're done reading this one, which does look better than the first two, so far at first glance I saw more code, I see more details, but Probably not today because we're already an hour and a half in. We'll probably be 2 hours in after this, which is probably going to be my cutoff. I still have to research this. This didn't help. Like, it may have pointed me in a couple directions of what to research, but like this didn't do what it, like, I don't feel like I've learned anything from this. If somebody else did, that's great. But like, I've already kind of looked at this solution a little bit. And when I say a little bit, I mean like the highest level surface area look at possible, and I feel like I didn't really learn anything new from the first 2 attempts at this. One thing I want to do before we get into that here is I'm going to link this page already because I want to put a note to start. And level 3 heading. And we're could not attach file like I did for the first 2 attempts. Instead, it looked up the source code on its own to provide the report. Okay, so deep research overview. In 2024, the 1 billion row Java challenge electrified the Java community. I don't need... This is another thing I don't need. I don't need the sensational language here, right? Like, I'm trying to study. I came to you with this. Anyway, let's go through what it thinks is an exhilarating sentence for us to just be captured by how well it words, right? AI words very well. It uses word very well. Good words. Good choice word. Word choice good. Like, shut up, AI. Catalyzing a wave of extreme optimization after... I don't think I would say that. I don't think this catalyzed a wave of extreme optimization efforts and setting a new standard for file I/O performance. I don't think most people know about this. I think that's just a lie, but the challenge process a million... Okay, we know what it is. Let's see. The technical achievement of the top solution drew from advanced topics rarely seen or applied in mainstream development. And this didn't change that. Parallel file I/O, file chunking, SIMD-based, single instruction, multiple data, parsing. I don't know why this was important, but okay. Hand-rolled data structures, Graal VM, native image compilation, garbage code. Okay. This report, hold on. We need to, okay. This report presents a structured, in-depth technical analysis of the winning approaches. Approaches? I asked for the winner. Right? The winner. The winning solution. Not winning approaches. The winning approach. I don't care who came in second. Whatever. Okay, the 1 billion row challenge, simple high. Okay. So input a billion row CSV file. Goal: for each station, determine the minimum, average, and maximum temperature. Output alphabetical by station name. Solution should only use one core Java. Wait, should only use core Java. Okay. That's fine. Process the files quickly as possible using the provided hardware. 8 cores, large RAM, RAM disk. At this size, several dozen gigabytes, efficient file I/O becomes paramount. Okay. Naive solutions spending milliseconds per file already run deep into the tens of minutes. Optimization not only involved algorithmic improvements, but also a deep understanding of Java's runtime, memory, and concurrency subtleties. That's all very important stuff. Let's see if it nailed any of it in a way that is just consumable by someone with an average level of intelligence, which is me. I would consider myself quite average. Okay. The winning and top ranking solutions uniformly exhibit a stack of orchestrated optimizations, each compounding performance improvements and tailored specifically for Java's platform. Well, that's a good idea when you're in a Java-only challenge, to do things the best way they'll work in Java. Essential. Okay. I like this table. This is good. This is one of the best things we've gotten so far, is this specific table. Parallel chunk processing. File split into chunks for concurrent thread-based parsing and aggregation. Very high performance impact. That makes sense. Memory mapped I/O. Direct mapping of file portions into RAM using mapped byte buffer for zero copy access. Very high. I get that. Using Java's vector API for branchless wide lane field delimiter detection. That, the way that's worded here, that does seem like something I care about. The first two times it said it, didn't really say it in a way that made it, you know, brought it back to file I/O and why I care about it, right? This one here, again, I understand it's high. We're not going to use unsafe, but there are things that are replacing it in newer versions of Java that we do have access to. So understanding why they're doing this, super important. We're not going to copy it though. Custom data structures, fine. GraalVM native image, compilation ahead of time to a native binary, eliminating JVM startup overhead. Not super important for what we're doing. Disabling garbage collection to avoid garbage collection pauses. Okay. Buffer sizing and alignment. And regular JMA async profiler perf analysis. I mean, fair enough. They put in profiling stuff that was required for the challenge to help them measure what was happening. We don't have to do that. Okay. I like that we have a code example in the first little bit. I do like that. I like, this is much better so far. So far, this is leaps and bounds ahead of the other two. Parallelization was the single greatest contributor to closing the gap between naive and high performance solutions. Who did this without, like, who attempted to do this on a single thread and thought that they were going to win? Like, I think it's very clear the only way. I mean, maybe for research, maybe they just wanted to know. And maybe there is some, like, trophy for best single-threaded performance. That could be cool. But, like, for the overall challenge, yeah. If you can do two things in the same amount of time someone else is doing one thing every time and there's a whole bunch of things to do, you don't just finish in half the time. You finish in, like, 0.0001% of the time. The more, like, it's not a straight comparison. It doesn't scale the same. It's exponentially faster. So yeah, of course. A leap so significant that the first jump in the stepwise optimization took his reference from 125 seconds to only 6 by just parallelizing I/O. That's a tongue twister for me this morning. Approach. Memory map the entire file. The input is mapped into memory using Java's NIO mapped byte buffer, or in newer Java, the Foreign Memory Access API. That's important. We have access to other things. Chunk partitioning. The file is split into n chunks, generally equal to the number of available CPU cores, commonly 8. Each chunk is assigned to a worker thread. Each thread's chunk boundaries are adjusted to align with the to align with line ends to avoid splitting CSV records and guarantee every line is fully processed by exactly one thread. In further optimized versions, chunks may be finer grained with atomic counters so faster threads can pick up extra. I mean, yeah, you have to. You have to. The way that CPU cores work now is that they're not all equal. You have to do this. Faster cores have to be able to handle faster workload, and slower cores need to chug along at the rate that the slower core is going to chug on. But not all cores are the same, and you don't know which one you're getting. So yeah. Example of partitioning pseudocode. Why didn't you just use the code? Okay. Number of threads, file size. We'll see if this, again, we can compare this to other things later now that we have it. So for each of those, so in this example, so maybe I'm just stupid. And that's where I always start with. That I'm the stupid one, even when I'm talking to a computer-based thing that maybe won't talk back to me. When I do this, so I need a way to like write this down. Hold on. We use crap.io here. Hold on. So we've got our 8 threads, right? So I got a chunk. This is my file, okay? Let's say we've only got 4. This is the whole file, okay? This is the entirety of the file. And so we're just, again, we're taking an easy example here, but let's say this will make sense here in a second. So I've got these lines here, and what am I doing with these lines? These are where the new lines appear. Okay? How does this code say, okay, I got a chunk size that is this long, okay? The next new line is here. Okay? How am I adjusting the start? So like in this chunk, do I just not care about this one then? And then maybe it looks more like this? So then this would scooch backwards, or does this scooch forward into the next chunk? You kind of see where my dilemma is here? Like what does it do? How does it recalibrate itself for the next one? So does it, I guess like the first one would have to say like, am I at the start of the file? And then when I get to here, I would say go find the first new line. And then on the second chunk through, I would say, okay, am I a new line? Read until I am a new line. And then at the end, I guess you just always do have to go forward. Right? Here, hold on. This is now becoming... Make these blue. We've got these boundaries, right? So, like, I don't fully understand how and where it would chop things up. It must always just, like, assuming this chunk go forward because this one would have had to go forward, and then it would just always have to go forward to the next one, basically, until end of file. So what you would end up with here... Now, see, this is really what I wanted this to explain. Was this that we just figured out right here is probably what it does. We can look at it later and try to find out. But, like, I don't think that's immediately obvious. There's also no way to guarantee this, that optimally partitioned chunks max or cache use, minimize synchronizations. I don't quite know what it means by that. Is that talking about, like, not needing to increment, like, thread safe atomic ints, or is that talking about, like, the synchronization of new line characters, like finding out that you have to go forward a bit into the next chunk? Trunking when paired with memory mapped I/O and careful chosen boundaries avoid sequential file read bottlenecks and enable each CPU core to parse and aggregate independently. So I still feel like we don't know nearly enough here, but that's okay. No, that didn't work, did it? So memory mapped file access and NIO versus IO. So that maps on really good to what we're talking about here, which is what we're actively researching, right? This is what we're actively looking at. So let's throw that over here. Let's do this. So that's not what I want. You go here, and then over here, you be here. There we go. Okay, so far this is the only one really worth contending with. So let's take this one seriously. This one, how do we feel about the parallel stuff? Let's deep research. Okay. The code example was pseudocode instead of just showing the example from the actual winning solution. The code example doesn't really show which... Can I make this even smaller? Yeah. Hold on. Okay. Let's put these up a bit. Doesn't really... Code example doesn't really show the important part. IMO. It shows how to start a new thread and calculate the initial chunk size, but then completely glosses over the actual solution, which is detecting the boundaries of that chunk. I think that's a fair criticism. Okay. We are going to say just going to change this here. Hold on. Parallel file partitioning. Okay. Next, we've got this one, which is memory mapped file stuff, and we will memory mapped file access and NIO versus IO. There we go. Okay. High-end solutions favor Java's NIO memory mapping to... Okay. Let me start over. I started reading ahead there. High-end solutions favor Java's NIO memory mapping to directly back data with native memory, affording high-speed random access to the file and leveraging the OS's efficient paging mechanism. Mapped by buffer. Maps file regions directly into RAM, avoids explicit I/O system calls after the initial page-in, speeds up reads, and allows for direct byte-level access from Java code. Comparison to I/O streams. While buffered input stream and buffered reader offer significant gains over unbuffered streams, they can't match the throughput of memory-mapped files for larger data sets, especially where random or chunked access is needed. Okay. Immediately, good summary, good high-level summary of why NIO, why mapped byte buffer is better than input streams. I say good high-level summary. I wouldn't even, maybe not even a summary, but close enough. The example given is just how to declare it. It's not really that useful. Probably, although not stated, pseudocode. So zero copy, immediate random access, OS level paging, memory mapping very large files requires sufficient virtual memory, and because unmapping occurs only at garbage collection in Java, special care, sometimes with unsafe or cleaner, is needed to unmap aggressively if resources are tight. Hints at a large weakness, which is that memory mapping files that are large may not be a good idea, as they will all need to be in memory No, wait. May not be a good idea. Because the file will only be unmapped at garbage collection for large files. This probably is not ideal unless you can somehow free the memory on your own. So far this is a better, but it's still not like what I wanted, really. Maybe I'm just picky, but okay, SIMD. SIMD CSV parsing with vector. Okay. Oh, this should be done. Heading. So, Java's Vector API, introduced in 16, enables efficient SIMD-style computation, parallel operations over vectors of data mapping directly to CPU instructions like AVX2 or ARM Neon. SIMD parsing, instead of examining one byte at a time to find delimiters. Okay, SIMD parsing. Instead of examining one byte at a time to find delimiters, a vectorized approach checks 16 or 32 bytes in parallel for matching delimiters. Load a slice of the input into a byte vector, compare all bytes against a target delimiter using a single instruction, extract the comparison to mask. Jeez, I can't read. Extract the comparison mask to quickly locate all matches. Mask-based parsing. Fast delimiter detection using bit masks without conditionals, suitable for CPUs with strong branch misprediction penalties. I mean, that's kind of hard to know when you're making something that's general use. What's this? That in here somewhere? Nope. An okay explanation of vectorized delimiter checking, but the sample code has an unexplained constant? I don't really know what species 256 means in this context. It is not explained at all. On CPUs with wide vector units, this produces orders of magnitude speedups for delimiters. Limitation: some SIMD code does not compile to native graphy images. Okay. SWAR, okay, they switched to SWAR, which is SIMD within a register. Okay. Okay. We are getting close to being done for today, guys. keep in mind, we're learning kind of a lot of like ridiculously high level concepts that don't really apply to anything. And the AI really is not doing a good job of describing a lot of this stuff. So we're just kind of getting word salad a lot of the time. Even if it's correct, it doesn't do a good job of explaining it. Okay. So once we're once we're done of this, we're gonna have to go do our own research and then compare it to what the AI told us to see if even in the end, like, this can still be all correct and still be a terrible explanation. Kind of like, you know, some teachers are bad. That's just a thing. They might know what they're talking about and still have no idea how to explain it to you in a way that is remotely digestible. That's what's happening here. This is a research screen. Hold on, let's tag this up here before we keep going. How's everybody doing today? I'm doing super good. So this is AI, Java, IO. Let's do 3 in a row challenge. Okay. And we'll grab the VOD link when we're done. So, for CSV, most lines are very similar, small size and structure. Parsing without if statements inside of the hottest loops. Okay. This is a lesson we could learn with mask-based byte operations, a trick inspired by high-end C++ parsers. Fair enough. If you can use a bitwise operation to glean the same thing as you can from an if statement, and that's significantly faster, I mean, sometimes you got to do it. Okay. Treat a memory word as 4 to 8. 4 to 8? Okay. 4 to 8 adjacent bytes. XOR the word with a mask where all bytes are the delimiter. So the... Oh, this is a fun one. Wow, that's... Again, this is a terrible explanation, but I understand this one. Give me a sec. So... Okay. I don't know why it has to be between 4 and 8. That's the weird part. So, XOR the word with a mask where all bytes are the delimiter. So bytes equal to the delimiter become 0. Okay? So, in order for us to... Oh, we're gonna go on a bit of a tangent here, but... Okay, XOR... I know a lot. Hold on. Except the ones who are dead. I'm gonna suck at explaining it. But there's no sense crying. So anytime they're different, you're going to get anytime they're different, you're going to get true. Okay? So basically, what we're going to do here is so every time, give me like, if I have, okay, we need crap IO again. Hold on. So instead of saying, is it the letter P? And then if it's not the letter P, go to next. Okay? Instead of doing this, where it's just this. No, I don't want a list item. I want text. Instead of this. No, it's not P. Okay, go to the next one. Is it P? No, it's not P. Okay, go to the next one. Is it P? No, it's not P. Okay. Well then. Yay. End. So like instead of this, where you're just going, is it this? 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 Instead, what it does is it takes a bunch of binary. Okay? So if we say that let's say that we have, you know, this text here. A, B, C, D, E, semicolon, J. Okay? Let's say that we got this here. So what this is saying is I'm going to turn this into binary, and I'm going to get a, you know, some kind of binary string out of it. We don't have to be accurate here, but we can just, you know, I've got some binary here. Instead, what this says is we have exactly this many characters. So I'm just going to do this. And then I'm going to do what's called a XOR. Does A equal this? No. Okay. Then the result is going to be, hold on. So when I do a XOR here, we'll copy and paste this one so I get the same size. Keep in mind that like one letter is not equal to one thing of binary, so there's going to be like more bits involved, but we're going to simplify this and say that we're just going to do 1 to 1. So is A equal to semicolon? No. Is B equal to semicolon? No. Is C equal to semicolon? No. D, E, is semicolon equal to semicolon? Yes. And then J is no. So instead of saying, am I on semicolon? Loop ahead. Am I on semicolon? Loop ahead. Instead, what I said is, if I take these two binaries and I do a XOR, the resulting binary is this. That means the second from the last position is my delimiter. So in like one operation, using a mask of what you're looking for and doing a XOR, it only returns a 1 in the position of the thing that you actually wanted. So that's kind of cool. Use a count. Trailing zeros are similar intrinsic to find the position of the first delimiter. So we get our data. The diff is this XOR, and then it does some silly things to find a count of the trailing zeros. Wait. Data. Great, that's a semicolon. Each set bit in mask marks a delimiter. Right, because diff minus broadcast this, I'm rusty on my bitwise operators. I would have to reread this. This is still true for what we're trying to do though. But was this a good explanation of that? I don't think so. I think if you already knew all that, you could come to this solution potentially on your own. But I don't feel like this is a good example. Like, explain it. It kind of explains the high-level one-liner concept and then gives you a bad example. let's see, uses bitwise operations to detect a delimiter. Using a mask and a Zor, you can detect where the delimiter is. Jeez, I can't even spell. That's not what I wanted. I don't even care enough anymore to do it. Okay, where the delimiter is. That's all. However, a better explanation of the actual operations would have been nice. For example, I can easily look this up, but in a deep dive research based question, I don't think it's crazy to expect that to be broken down. A lot of people just don't work with bitwise operators at all and don't even know how Zora works and just would be completely lost by this. So I think a bit more instruction would have been nice. I don't think I want to take notes on this part. I really don't care about their own data structure. And we're running out of time as well. I don't feel like we're not going to do this. Native image compilation. No JVM dependency. Okay, so that's probably not going to help us. But we can try with GraalVM. But this isn't really coding stuff. This is configuration and how you're going to compile it. In Java, the garbage collector adds overhead by pausing application threads to reclaim unused memory for short-lived one-shot programs like 1 billion row challenge, where memory is pre-allocated, the program exit releases all resources. This overhead can be eliminated by switching to Epsilon garbage collection. Epsilon garbage collection was introduced in Java 11. Epsilon is a no-op garbage collection. It only allocates memory, never reclaims it. When memory runs out, the program edit memories and exits. So it was able to do this here and say garbage collection GC. But instead, it just says out of mana. Oh, memory, right. Be consistent, come on. Now for well-provisioned short-lived programs. That's not really something we can do. Unsafe. This could be something we care about. No feature in the winning solution is more controversial or more potent than the strategic use of unsafe. This API enables direct off-heap memory access, manual memory management, and bypassing of Java security checks, including array bounds, type safety, and built-in garbage collection tracking. Application buffer access. Rather than copying bytes in and out of heap-based arrays, which are bounds checked and garbage collection tracked. Contestants allocate memory blocks with unsafe allocate memory, process data with get byte, put byte, and free manually. byte scanning, serial or vectorized access to large slices of memory-backed CSV data for parsing or delimiter detection, memory cleanup, unmapping mapped files, releasing memory when done, and preventing spurious out-of-memory errors, sometimes associated with delayed garbage collection of buffers. I mean, okay, that's a pretty weak, I would say, like, explanation. Like, I feel like they make it sound a lot more important than what they're portraying here. Like, they say how important it is, and then they're just like, oh, well, I mean, buffer access, scanning, and manual cleanup. They don't really go the extra mile to explain why this is better. Over which overhead specifically? I mean, this is something that's impossible in pure Java isn't necessarily a good reason to use it. Custom off-heap data structures could be a benefit. Memory safety violations pretty big. Non-portable, that's not good. Yeah, it's not recommended, so I don't care too much about it. We're not going to use it. This we're probably going to care about, though. This will probably be the last thing we get into before we end here. Buffer size optimization is classic, often underappreciated. System calls are expensive, they sure are. Large buffer sizes reduce the number of calls and improve throughput up to a plateau determined by the file system, OS, and hardware cache sizes. Many Java classes use an 8K buffer by default. Ideal size. Empirical evaluations and benchmarks suggest buffer sizes between 32 and 64K strike a good balance. Okay. For large file reads in most systems, as they fit reasonably into CPU's L2, L3 cache and match disk I/O block sizes. That's a good thing to know. Let's take that. We are down in I/O land. I/O buffer sizing and tuning. Explains that bigger buffers mean less system read writes, which is faster. Default buffer sizes in Java are usually 8 kilobytes, but Copilot says that empirical data suggests that 32 to 64 kilobytes is the sweet spot due to it matching well with L2, L3 cache sizes, and also disk block sizes. That's a very important thing to understand. I don't know if those numbers are right, but understanding that the ideal size is something that fits in an L2, L3 cache and matches disk I/O to some extent, like usually a multiple of is pretty good too. Tuning methods, test with, okay, sure. For memory map file I/O, the OS already manages paging efficiently, so the buffer is virtual. Tuning applies mainly to input streams and manual chunk reads. Okay. The AI then seems to contradict itself. And say it doesn't really matter at all. Cool. For memory mapped things. Which is what we're talking about, is memory mapped things. Okay, I don't care about the profiling. Let's put a couple of quick links here. Techniques and key optimizations.
You fight well in the old style.
Techniques and key optimizations. And I also want the summary table. Where is that? Summary table. Oops. Summary table key optimizations and their impact. Okay. So the file chunking was 40x, memory was 4 to 5. This is, I do like seeing this. Unsafe brought us 25% faster, but wow. Okay, 200 milliseconds saved, I don't really care about. Yeah, that's cool. Code insights. To ground the above concept, here are the key excerpts. Okay. That seems like another good thing to grab. Okay. So, here we're going to do our deep research, and we're going to go down to code insights. Go code insights and representative snippets. I did not know what to expect, but this is kind of where we're going to end it. Actually, let's... Okay, that's fine. This was good, though. I feel like we did learn some things. Use Copilot to analyze the 1 million. Okay. And these were all what? Threes? Yeah. Let's put a conclusion here. Conclusion. This took 2 hours. And I learned a little bit. I probably would have learned a lot more not using Copilot. There have been other people who explain this code in more detail and in a more accessible and digestible way. Copilot scratches the surface, but ultimately lacks detail for the specific solution. Meaning that it is happy to toss concepts in your face, but does not show them being used in the actual solution. Instead, it resorts to its own pseudocode, often picking useless parts to highlight. So like just showing you how to set it up versus how to use it kind of thing. That was interesting. That was yeah. That's not what I wanted, but it's more or less what I expected. Copilot's not, I don't know, again, maybe I'm just old man yelling at clouds, but like, I'm not a huge fan of, you know, what we just kind of went through. I think that there are much better ways to get that information. I'm just going to make an ending screen thing because I didn't have that last time either. So hold on. Let me make an ending screen and then I'm going to be done. And I hope you guys have a good rest of your day. I've got a bunch of other stuff to do, so I'm going to go on my way for that. Thanks for watching is what this will say, and I believe the font is called Pixeloid? Yeah. Got it smaller. But thanks everyone for coming out. I hope you enjoyed it. We are getting slowly closer to actually make... yeah, we'll delete that. We're slowly getting closer to what we want, which is making this chess thing. But I usually end up doing a lot of research in between. So I hope you guys actually enjoy going through a lot of this stuff. Because there's a lot more to go through. There's a lot more to learn. We're not going to be doing most of it with AI, though. Most of it's going to be actual research. I just thought this was a fun, kind of low-effort stream. I wish I would have learned a bit more from it, but we got some good notes. So, yeah. I will see you guys in the next one.